Okay, 5, 4, 3, 2, 1. Thank you. Okay, cool. Okay, so raise your hand if you think the answer is A, B, C. Thank you. Okay, so definitely not D because yeah, things are discovered by accident, like penicillin, which came from penicillium, the bacterium. But anyway, he made accurate predictions that would allow for scientists to then plug in these extra elements that we had not discovered yet. Because people have to discover elements or make them. They don't just come across them most of the time. So they discover them through some sort of analytical technique or in ores, like in a mine and stuff like that. So the periodic table is very special because all the groups come together and they have common properties. So everything in group 1, where's group 1? You can tell me. Are groups, do they go down the periodic table or do they go across the periodic table? Down. Groups go down. So group 1 is going to be everything here. So they all have common characteristics, usually common physical properties and common chemical properties, specifically chemical properties, because they all have common chemistry, like it's about mainly where their electrons are. So they have common properties and how they react. So all of group 2 has similar properties. All group 3, which is here, all have similar properties. 4, 5, 6, 7, 8. These guys in the middle, those are all transition metals, and they have a funky kind of characteristics. They have electrons in weird places. We're going to learn about them more later, but the groups that I highlighted, these like columns here, and then these columns here, those all have specific characteristics. We're going to learn some of those today. Okay, so that's a quick preview of that. Keep your notes because we're going to watch one more video. You're going to add to that, okay? And then we're going to go quickly over mixtures again, because in our lab today, you are actually going to be separating mixtures, okay? So we have I want first just give me a brief explanation between the difference between mixtures, solutions, and compounds. So quick and easy. What is a mixture, Zachary?
A mixture would be a blend of two substances changed.
Okay. Do this. Let me figure out why this is not writing. It's blinking. Okay, I'm not going to write this down. Maybe I will. Okay, so 2 or more, what?
Substances.
So pure substances, right, are specific. So 2 or more pure substances with own properties. Okay, so whatever those properties are, they're going to maintain them. What is the difference between them, or what's specifically a solution, Hannah? Oh, okay, that works. Go for it.
Like liquid that has the evenly distributed particles in it.
Okay, so it's still 2 or more pure substances. One is probably a liquid, because a solution is generally an aqueous solution form, like liquid form, and then one is generally dissolved in it. You can have 2 liquids dissolved in one another, but one at least is usually a liquid. And then our solutions can either be, usually solutions are homogeneous solutions. Homogeneous means what? Same, it looks the same throughout, right? You cannot tell the difference. And then compounds are just a type of pure substance with what in it? What is a compound made of? Yeah.
Elements.
Right, so 2 or more elements. And they can be the same elements. Like, for example, O2, that's a compound. And it has 2 oxygen atoms, or 2 of the same element, but there's at least 2 of them. So that's just a little bit more hitting the highlights of our differences there. Okay, so if I have a mixture, we have a mixture in there, we know that it has 2 or more pure substances in it. What were some of those techniques we could use to separate these things? You learned about them in off of problem set 2. Yeah.
Electrolysis?
Okay, electrolysis actually totally tears the atoms apart. That's a chemical change. That's like a chemical ripping apart of the atoms. Tell me something else. Yeah, Danielle.
Filtration.
Oh, okay, so yeah, filtration. Danielle, you got something else? Distillation. Anything else?
Maybe like what we did in the lab the other day, about like evaporating.
That was something that we talked about specifically as a chemical change. So you can evaporate something off from a solution. So I'll say evaporation of a solution, S-O-L-N, a solution for me. And that would separate the liquid water from like salt. so I'm just going to be more specific there. What's our lab on today? Do we remember? Say again? Chromatography. Okay, so we're going to talk about chromatography and how that works and why that's different than these. And then we got, oopsies, quick video, and then we'll move on. I'm really not this computer illiterate. I'm just having some troubles today. Okay. So, let me scroll down for us. So these are some other ones, and some of them you might be familiar with. So we had evaporation kits, so a solid and a volatile or non-volatile liquid. We have centrifuging. You guys know what centrifuging is? Have you ever seen like on CSI where they put some samples of blood and contain it at cylinder or circular, and then they spin it around really fast. It separates liquids and solids. It's called centrifugation. So that's what that is. Filtration, we just talked about. Chromatography, talked about. Distillation and sedimentation. That's just let stuff settle. Foam pretty easy. So those are just a couple more. But the ones that we talked about are the more important ones. Okay, so let's watch this quick video from Law of Conservation of Matter. Take down a couple of bullet points. Okay, I'm not going to say a specific number. This video is it's got review in it, and it's cool because at the very end it kind of talks a bit more about life in general.
Where does all this stuff come from? This rock, that
Sorry,
cow,
I have it on
your heart,
speed mode.
not the things themselves, mind you, but what they're made of, the atoms.
Sorry, I don't listen to YouTube videos on normal speed. Let's go normal speed. Here we go.
Atoms that are the fabric of...
Let me just refresh this. I'm speedy here. Yeah, from last night.
Where does all this stuff come from? This rock, that cow, your heart. Not the things themselves, mind you, but what they're made of. The atoms that are the fabric of all things. To answer that question, we look to the law of conservation of mass. This law says, take an isolated system, defined by a boundary that matter and energy cannot cross. Inside this system, mass, aka matter and energy, can neither be created nor destroyed. The universe, to the best of our knowledge, is an isolated system. But before we get to that, let's look at a much smaller and simpler one. Here we have 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. With a little energy, our molecules can really get moving. These atoms can bond together to form familiar molecules. Here's water, and here's carbon dioxide. We can't create or destroy mass. We're stuck with what we've got. So what can we do? They have a mind of their own. Let's see, they've formed more carbon dioxide and water, 6 of each. Add a little energy, and we can get them to reshuffle themselves to a simple sugar and some oxygen gas. Our atoms are all accounted for, 6 carbon, 12 hydrogen, and 18 oxygen. The energy we apply is now stored in the bonds between atoms. We can re-release that energy by breaking that sugar back into water and carbon dioxide, and still, same atoms. Let's put a few of our atoms aside and try something a little more explosive. This here is methane, most commonly associated with cow flatulence, but also used for rocket fuel. If we add some oxygen and a little bit of energy, like you might get from a lit match, it combusts into carbon dioxide, water, and even more energy. Notice, our methane started with 4 hydrogen, and at the end, we still have 4 hydrogen, captured in 2 water molecules. For a grand finale, here's propane, another combustible gas. We add oxygen, light it up, and boom, more water and carbon dioxide. This time we get 3 CO2s, because the propane molecule started with 3 carbon atoms, and they have nowhere else to go. There are many other reactions we can model with this small set of atoms, and the law of conservation of mass always holds true. Whatever matter and energy go into a chemical reaction are present and accounted for when it's complete. So if mass can't be created or destroyed, where did these atoms come from in the first place? Let's turn back the clock and see. Further, 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 too far. Okay, there it is. The Big Bang. Our hydrogen formed from a high-energy soup of particles in the 3 minutes that followed the birth of our universe. Eventually, clusters of atoms accumulated and formed stars. Within these stars, Nuclear reactions fused light elements such as hydrogen and helium to form heavier elements such as carbon and oxygen. At first glance, these reactions.
So what they're saying right here, and this is just kind of really neat. So we know hydrogen is the smallest element, yeah?
Yeah.
How many protons does it have in its nucleus? One, right? So when you fuse one proton from hydrogen's nucleus and another one, you get two. Well, that 2 proton number means it's not hydrogen anymore, it's helium. So then if you take helium, which has 2 protons, and another helium, which has 2 protons, you fuse that together, you get something with 4 protons in it, which is beryllium. Yeah, beryllium. So you can get fusing things together. So you can build lithium, beryllium, carbon, nitrogen, oxygen, fluorine, blah, 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 blah. You can build these things until you get to really heavy things like iron. And that's what this is showing you. So I'll scooch back just a second.
And helium to form heavier elements such as carbon and oxygen. At first glance, these reactions may look like they're breaking the law because they release an astounding amount of energy seemingly out of nowhere. However, thanks to Einstein's famous equation, we know that energy is equivalent to mass. It turns out that the total mass of the starting atoms is very slightly more than the mass of the products, and that loss of mass perfectly corresponds to the gain in energy, which radiates out from the star as light, heat, and energetic particles. Eventually, this star went supernova and scattered its elements across space. Long story short, they found each other and atoms from other supernovas, formed the Earth, and 4.6 billion years later got scooped up to play their parts in our little isolated system. But they're not nearly as interesting as the atoms that came together to form you, or that cow, or this rock. And that is why, as Carl Sagan famously told us, we are all made of star stuff.
So that's just a different perspective of chemistry, right? So with that, what I wanted you to get from the back side of the video, that's the last part, was about energy. And so when we talk about law of conservation of matter, law of conservation of mass, that's kind of what we are narrowing down on because it's tangible, right? It's in our hands, we can mass it out. It's hard to really confirm the law of conservation of energy, but it is also a law because all matter is, they're particles, but those particles have energy. So they're all interrelated.
Can I have Sally Holloway to the front office?
In just a few minutes, thank you.
Okay, thank you.
Okay, so these are all interrelated. So what's funny, and this is, I saw this joke on Pinterest, when they have the go green, if you're the last living room, turn lights off, conserve energy. Joke's on you, energy's always conserved, right? Doesn't have to turn light off or on. Electrolytes saves energy, doesn't conserve energy. Energy's always conserved. So that's just a little tidbit of information for you. Let's go. What's here? No, we don't need that. Okay. So let's go to our lab. And let me just give you a quick preview of homework for tonight, okay? So homework tonight says complete half of the unit review. And half the unit review is in your packet, right? A lot of repetitive stuff. You'll see a lot of stuff from unit concept 1, 2, and 3. What I would do tonight, spend about 30 minutes or less going through the things that are easy for you. Skip the things that are hard for you. That's what you want to ask me or up here tomorrow in class. Because tomorrow is unit review day, meaning we'll finish up any activities you didn't finish up lab questions you didn't finish, and then we finish your unit review. And my motivation for you is that if you finish your unit review entirely by the end of class tomorrow, you get 5 extra credit points on that assignment. So it's called just part of your portfolio check. So you'll get an extra 5 there. So in the portfolio check, speaking of, in Unit 1 notes that you've taken, the bullet pointed notes from the 3 videos now that we've watched, so the 6 plus the 10 plus whatever you just took down here, the unit review that you are completing tonight, and then the flipper card. The flipper card is simply a couple of things that you just have a hard time remembering, and that's what I want you to write there. It might be the King Henry died by blah, blah, blah. It might be 1 centimeter cubed is equal to 1 millimeter. It can be little things that as you're looking through your notes, you're like, oh, I just can't remember that. Write on the flipper card. So remember, at the end of the year, you have a nice flipper chart, and you know that yours does not have to be pretty and colorful. You're just going to have one note card per unit. And it's just personal, it's up to you. I look at it for completion. Something should be on it, even if it's a picture of water. Okay, here's the other. And I can post this later too to see all the things going on. So here's the flow of how we need to proceed. we are going to start a lab, but as we start the lab, it has about a 25 to 30 minute wait time because it's chromatography and it takes a while for the solvents to move, which is, I'll tell you what our solvents are in a second. So during that, you're going to take some notes on the periodic table and then finish up your lab after the results have occurred. So I'll come back here if I need to in a little bit. So let me show you the chromatography lab first. Okay, so in the lab, I have laid the labs out for you. Actually, they're not in your notebooks. You need to read so take 5 minutes, read the beginning. If you want to pull out a piece of paper now and like write down what you need to do for the lab, that might be a good idea. You're just going to write like a 2-sentence summary of the purpose and the background of the lab. Then I've already placed dies at your tables for you, so it says choose one die and complete both trials on it. I already chose the die for you. It's at your lab station. I have already cut strips for you. I have cut these chromatography strips for you. And what you need to do is cut the V in the bottom. Because basically what you're going to do is you're going to put your chromatography strip in some solvent, like this. Okay, so this is a beaker. You're going to put your solvent about here. And your solvent should not touch where you have placed your ink of your dot of ink, which is your dye. So I've already cut this. You just need to cut the V shape. You're going to place a dot of dye there. The solvent is going to sit here and it's going to use capillary action. Remember what capillary action is? What is that? Capillary action. As a tree get water to the top of its, yeah, go for it, Anna. Polar. Right. Water is polar, right? We all know this. What does polar mean? It means that H2O has on this side more electrons, on this side more protons. Actually, not more protons, less electrons. But it has an opposite end. So like the north and south polar opposite ends on water means that it is polar. So anyway, the solvents are going to travel up. You have 2 different solvents. Some of you guys have ethanol. Some of you guys have isopropyl alcohol. Everybody's going to have a second trial of just straight water. Okay, so when I say 2 trials, one of the things is going to be an alcohol, and the other thing is going to be water. And then after that, just don't let the solvent touch. It will slowly go up. I do have some popsicle sticks that you guys can hang on top of the chromatography paper and tape the chromatography paper to it so it doesn't like lay down in the fluid. You just want it to touch the fluid. I'll help you as you go. Otherwise, you're going to sit there, let it do its job, read ahead a little bit, and as you read ahead, you're going to find out that you can't really go on anymore. Then you're going to go to my website and or scan the QR code I have here. I have them taped around the room too. You'll see like 5 or 6. There's another one here. Scan that. There's about 6 pages of notes to take there. Okay, it won't take you the whole time probably. And then other than that, you're going to finish up the lab. And if you have time today, or let's see, or tomorrow during your review day, you guys saw my periodic table of QR codes out there? Outside my room? It's huge, yeah? You can scan any of those. They're just interesting videos about the elements, and you can write down 10 to 15 fun facts for 2 extra credit points. Okay, so have fun if you want to with that. So, questions on our flow here. What are you starting? Lab setup. Then you're going to do what? Notes, and then you're going to finish the analysis in the lab. And as you finish your lab, I'll pull this back up later. Sorry, I gotta scooch through here. As you finish, as you finish, you're going to share your data by taping your chromatography strips to like just a piece of paper and putting them like around the room because other people might need to see your data to answer some of the questions because not everybody's doing ethanol and not everybody's doing isopropyl alcohol. Okie dokie. I'll explain more as we go. So, same lab groups, let's go. Oh, probably wrong that one is on your desktop on the right. You're writing a purpose or a statement first of the purpose of the lab or background.